This is the lecture recording for Friday, March 31st with Dr. Franklin, covering the last part of section 16.2. I want us to begin by looking at the properties of logarithms, and there's a few properties that come directly from the definition of a logarithm so that we can understand why they work just by looking at what a logarithm is asking for. So in the very first one, in the blank next to log base b of 1, we know that this has to be 0. Because this question of what is log base b of 1 is asking the question of what do I have to raise b to in order to get 1. And as we know, since b to the 0 is in fact 1, then the exponent, of course, is the answer. 0 is what you get. Which means no matter what base, assuming the base is a positive number, that you have in the logarithm, log base b of any base of 1 is going to be 0. So the output of the logarithm, when you plug a 1 into it, is 0. On the second one, if you take the log base b of b, where b is any positive real number, and of course not equal to 1, then we're asking what do I have to raise the base to, b, in order to get to b, and the answer is 1, and that is because b to the first is itself, so the answer is the exponent, and 1. On the next property, if we have any positive real numbers x and b, if you take the log base b of b raised to the x power, the answer is x. In fact, x is also the answer on the second question, if you take b and raise it to the log base b of x. The first one is pretty obvious why, because if you're saying b to what power is b to the x, then x is the answer to the question you just asked. But the real reason is because we defined logarithms to be the inverse of the exponential function. And whenever they're inverses, they essentially cancel each other out. Since logs and exponentials are inverses of each other, then we see that they end up canceling each other out. On the last property, just keep in mind that if you have a log base b of x equals a log base b of y, then the only way for that equation to be true is if the inside of this logarithm, that is x, is equal to the inside of this logarithm, which is y. Then x is equal to y. What this tells us is that if I have a log on one side and a log on the other, and that's the only thing on each side, that I can simply mark out the logs, cancel the logs, and I'm left with just x equals y. That's how I would solve that kind of equation. Now let's use these properties to answer a few questions. First of all, if I ask you what is log base 9 of 9, using property above, if I back up, property number 2 says that log base 9 of 9 has to be 1. You can do that in a calculator. You can do it by thinking of it in terms of the definition of the logarithm, what I called the spiral doohickey in class, or just recognizing that's property 2. If you take the base and the inside of the log and they're the same, then the answer is 1. Log base 8 of 1 has to be 0 because 8 to what power gives me 1? The answer is 0. Now on both C and D, I want you to recognize that the base of the logarithm 4 is the same as the base of the exponential expression. On D, the base of the exponential expression, 6, is the same as the base of the logarithm. When you take a log of an exponential and they're the same base, they cancel, and you're simply left with the exponent x plus 2. Same is true for the second one. If you raise an exponential to a logarithm with the same base, they cancel, and you're left with just 9. Example E is the final example from the last property that says when you had the same log on both sides, you can essentially cancel them out. What you end up with is the fact that x has to equal 41. So for very simple logarithm equations, we can solve them by getting a log equal to a log, and then by property 4, the logs simply cancel out. Alright, the last thing I want to do in this short first video is to talk about the change of base formula. The change of base formula is what allows us to use our calculators to find logarithms that aren't in the calculator. Remember that your calculator does not have a log base 5. It only has a natural log and a common log. So in order to find the log base 5, we're going to use the change of base formula. The change of base formula is as follows. If you want to find log base b of x, you can do that by finding log of x divided by log of b. Always. That is guaranteed to work, that the log of x over the log of b, where that log is the common log here, is the same as log base b of x. Take the log of the argument, the log of the number, divided by the log of the base. Actually, that also works if you use the natural log. You get the same answer either way. Surprisingly, that's always true. So let's try that. On the next example, I want us to find log base 5 of 40. So I want to know, what do I have to raise 5 to in order to get 40? 5 to what power is 40? Now I know it has to be more than 2, because 5 squared is 25. But I also know that it has to be less than 3, because 5 to the third is 125. And I'm looking for a number between 25 and 125, which means my answer has to be somewhere between 2 and 3. But how do I know exactly what it is? Well, I use the change of base formula. That's log of 40 divided by log of 5. If you want to find log for any base, that's how you do it. Take the log of the number over the log of the base. So I plug that into my calculator, and I got 2.29 approximately. I rounded, but give that a shot. Plug it into your calculator. Type log of 40 over log of 5. This is what you get. And you can check it. If I take and raise, note, 5 raised to the 2.25 is approximately 40. It's approximate because I round it. If I go more decimal places, then I will have the same or a closer value to 40. The last example I want to do on this first part video is to rewrite the following expression, 7 log base 3 of 2x plus 9 in terms of natural logarithms. So what I'm going to do is I'm going to turn this log base 3 into natural logarithms using this property right here. If I rewrite that log base 3 as the natural log of the argument over the natural log of the base, I get this. You take 7 and then replace this log with natural log over natural log. Natural log of the inside 2x plus 9 over natural log of the base, which is natural log of 3. So that's a correct answer. I would probably want the final answer written where you put the numbers together and the formula together. So you might write it as 7 over natural log of 3, which is a number in your calculator if you calculate it, times the natural log of 2x plus 9. But either one of those, either one of those is correct.